what ECG is. Almost 18 million people annually die from different heart conditions and cardiovascular diseases, and electrocardiogram or ECG is one of the best non-invasive diagnostic tools that we have to assess the heart's performance, rhythm, and overall health. We have different kinds of ECG recordings, out of which a standard 12-lead ECG is considered the gold standard. These 12-lead ECG can be recorded by attaching 12 electrodes to the body, as you can see there. And out of these 10 electrodes, we get 12 recordings. That gives us information about heart's electrical activity across different angles. So if you look at this short video, you can see that by looking at one individual heartbeat ECG signal, you get information about specific parts of cardiac cycle, and that's why looking at these time series can be very informative for cardiologists as one of the initial assessment steps. Oh, but there are some complications associated with this. As you can imagine, attaching 10 electrodes to the body whenever you go to a clinic or hospital is not going to be comfortable, especially for long-term monitoring. So also you have 6 chest electrodes that are a bit harder to attach because of their proximal distance, and you're going to have more noise because you have 10 electrodes attached to different body parts. And we have a lot of personal devices that, if you think about the long term, if we could get these helpful data from those personal devices, it's going to be very helpful for people to have their personalized heart monitoring device. So a lot of researchers have asked, can we get this helpful information for cardiologists from a limited number of leads with an easier setup? They have used different linear and nonlinear model to get the standard 12-lead ECG from different inputs. In this specific study, we are interested in creating the 12-lead ECG from a limited number of 12-lead ECG sets, like lead 1, 2, 3, or something like that. We use 2 data sets. The first data set is a non-public data recorded by our colleagues here at Baylor College of Medicine. It has 15 patients with PVC, which is a heart condition. Each patient has 1 to 3 hours of recordings with the sampling frequency of 1 kilohertz. To give you an idea of how big this data is, I've provided this table which shows how many heartbeats we have for each patient. The second data set is a public data. It's PTB Diagnostic ECG Database. It's a larger data set with 290 patients. Each patient has 1 to 5 recordings with a total of 549 records. The sampling is 1 kilohertz again, and this is a diverse data set. It has patients with different cardiac problems. As you can see, we have different diagnostic classes, and you can see the number of patients with each problem in this table. So this diverse data set helps us to show that our algorithm is not just specific to healthy heartbeat, and it can be generalized to a specific heart conditions. To simplify the methodology, it has 3 main steps. The first one is pre-processing, basically getting ready data to be fed to the model. So we have these continuous looking ECG recordings, 12 lead across time, and we filter this to get rid of unwanted noise and segment the heartbeats into the recordings into individual heartbeats. And then to get a better representation, we transform data into time frequency domain just to get more information out of it. To avoid working with complex values, we divide these STFD data, short time Fourier transform, into real and imaginary parts. So we're going to have this nice looking 2D representation for each heart. So I mentioned that we're interested in reconstructing 12-lead ECG from a limited number of leads from the 12-lead ECG again, but the main question is, what can be those input leads that we want to work on? A lot of studies use 3 leads as input, and one common choice is using lead 1, 2, and one of the precordial or chest leads. So we also decided to use 3 leads as input, but the main question was, what 3 leads should we pick? So if you consider like all the 12 leads, picking 3 out of 12, that would give us 220 different combinations that we had to pick from. But looking closer at ECG recordings, it's obvious that 4 out of those 12 leads are redundant, meaning that they're a linear combination of lead 1 and 2. So we set those aside. Now we have 8 leads to pick 3 out of. That would give us 56 combinations. And we thought, what if we don't want to limit ourselves to one specific input set? What if we want to have a model that can work with all these 56 possible input leads? And we tried that. So we added one sort of identification. I refer to it as input lead map to each set of different choices of 3 leads, just to tell the model what leads are being fed to it for that specific sample. Now let's take a look at the overall flow of the model that we have so far. This is just one specific example I randomly picked. We have 3 leads as input, lead 1, 2, and V1. We transform them into time frequency domain just to get a better representation. And then we feed them to an encoder-decoder CNN. At the end, we get the information on 12 lead ECGs in a CFD domain, and then we convert them into time domain just to get that nice looking signal that is familiar for cardiologists. A closer look to our model, it has encoder-decoder parts with CNN blocks in it. And one might ask, why? We are using CNN because we have this image-like 2D representation, and CNN works really well with that kind of data. And we are also including encoder-decoder structure because if you think about it, all these 12 leads are recording the same organ's electrical activity. So it might be logical to assume that all these 12 leads have some shared lower dimension latent space, and that's what basically encoder-decoder does, finds that shared space and regenerates from that. So we are more interested in personalized healthcare. That's why we are reporting a patient-specific model, meaning it's best tailored for each patient to have the most accurate results. We use each patient's half sample for training and the rest for testing. We use all the patients from the first data set and 70 randomly selected from the second one. And because this is a regression task, we use RMSE, root mean square error, and Pearson correlation coefficient to assess the performance. So RMSE closer to 0, the better, and Pearson correlation coefficient, we wanted to get it close to 1 as much as possible. So here I'm representing the results for the first data set. You have patient's ID on the x-axis, and you can see average correlation coefficient box plots, and RMSE plots. We have 2 columns data, gray and orange. And so as I mentioned earlier, at first we attach some sort of identification to each input to tell the model which leads we are feeding it, but we didn't include them for a set of experiment, and it turns out the model didn't need those. So we didn't include them from the rest of the results. Looking at the values, it shows that we are getting almost really close to 1 values for correlation coefficients, and shows the success. So we thought the 3-lead reconstruction works. Let's try using 1 because several studies do. And here you can see the results for 1-lead reconstruction. We use different leads and feed them to the model, and then we try the general model that could work with any of these 1 leads. And looking at the average, we can see that the 1-lead reconstruction is almost following the 3-lead reconstruction results. Here are the results for the second data set. We made sure that those randomly selected patients cover a wide range of diagnoses in the data set so that the performance is just not dependent on a healthy heartbeat. And again, the average shows high correlation coefficient and low RMSE. To give you an idea of what these correlation coefficients actually look like, I presented 3 randomly selected figures. The orange traces are the reconstructed signals by the model, and the blue one are the original traces. And as you can see, they're almost perfectly matched. There are some discrepancies, especially in the first one. You can see like AVF, we have a higher peak in the original trace, but the most important parts of the heartbeat are preserved and reconstructed. At the end, we compared our results with recent studies. You can see their choice of input leads, technique, and average correlation. We outperformed these studies, and we added the flexibility of actually not having to pick the input before training the model. So this model can work with any of the input leads that you have available to you. So to conclude, we showed that Encoder-Decoder CNN model with the specific methodology that we developed can be a good pipeline to reconstruct 12-lead ECG from either 3 or 1 ECG lead. And there's a lot of promise, because if we can get high accuracy reconstruction using 1 lead, then we can have our own personalized monitoring, heart monitoring with us, because we wear watches. So at the end, a special thanks to my amazing advisor, Professor Ajang, and my great co-authors, Dr. Banta, Post, and Razavi. Here are the references. Thank you so much, and if there's any questions.
Is the dataset available for public?
Sorry, I didn't get that.
Datasets available online?
So the first dataset is not available yet, because just the policy of the hospital, they haven't anonymized it yet. But the second data is a public dataset on PhysioNet.
Okay. Did you test out all the dataset in Python or any other program language?
This is just, we code this in Python. I didn't use any other.
Okay, we see the multiple output side results, right? So the results from the, how you compare the data sets?
Oh, so in the comparison table, sorry if I didn't get your question first. Let me move back. So in this table, we decided to pick the same data set. So we are reporting the results using the PTB data set, but it's never possible to actually make sure we are using the same specific patients and same training and testing, but this is the best we could do, picking the same data set as other studies and perform the results on that.
So you didn't test the data set, just to take the result, see visually, and make the result, right? You didn't give any algorithms or anything to get the output, compare the like waves and all, right?
I'm not sure if I get the question. Sorry about that. Maybe we can talk after that.
Sure. Thank you.
Yeah, thank you so much. Sorry that if I wasn't.
Any other questions?
Good afternoon. Myself, Puneet. I'm a postdoc fellow at MD Anderson. I have a question. In your study, what is the ground truth?
So the ground truths are the actual 12-lead ECG that was recorded, and we pick a subset of those as input. For example, we use one. Let me go back to maybe the last slide. Okay. So the ground truths are the actual 12-lead recordings that we do have in the data set. Those are like real recordings that we have. And what we train is that we feed the model with, let's say, 3 leads out of those 12, and reconstruct a set of 12 leads, and then compare those 12 with the actual trained recorded data that we have. So the actual 12 leads recorded from patients in the data set are going to be the ground truths. It's a regression model. We have those as our ground truths. We reconstruct those and then compare how similar the traces are.
Okay. So it's mean like you are passing 3 different signal and getting 12 different signal as output.
Exactly. And we compare those 12 lead at the output with the real 12 lead ECG recorded from the patients.
Okay. Second thing is that you are using encoder-decoder architecture for this signal reconstruction, right? So have you checked about like this architecture used for noise reduction? So is this model like smoothing the peaks of a signal or not?
Can you repeat the question part
Okay,
again?
so the encoder and decoder architecture used to reduce the noise in the signal.
Mhm.
So is your method is like smoothing the signal at the output layer or not? Is
So no, we don't do any post-processing after the model, if that's your question. We do perform some noise removal before actually working with this signal, just to get rid of Van der-based noise and like other movement noise and motion noise like that. But we don't do any smoothing at the end of the data, at the end of the process for data.
my question is your model doing that?
The encoder-decoder part, I don't think that they do that, not for this application. I know that it can be used for noise removal, but I don't think that my model is focused on doing that here.
Okay, thank you.
Trying to do that, let's say.
One last question.
Here, this one? Okay. Just tell me when to stop.
Hello. Perfect, great work. Thank you so much. I have two questions, please. One about this study and what about the future studies. This one, have you compared with what we already have commercially, like the Philips machines, is ECG machines that can actually give you a diagnosis like instantly, and I think it's fairly accurate. Have you compared with it or not? And
Not-
the second, so sorry. And the second one about the future data. What about the Apple Watch or the smart watches, ECG? What about this data? Because I think that's tomorrow. These kind of machines, I think it starts to vanish, something like that. Because nowadays everyone has this Apple Watch and even can send my data to my cardiologist in a snap actually every day. Thank you.
Both great questions, thank you. So we haven't to answer your first part of the question, no, we haven't done that yet, but that's one of the steps we are considering for future direction. And the second one, we are absolutely interested in getting data from Apple Watch or similar personalized devices. We weren't able to do so yet, but that's going to be the main interest we have for this project, because as you said, we have this personalized device on us all the time. If we could actually perform such an algorithm on those devices that we have, we can get a real good personalized report of our cardiac system and its performance. We can get like, I was asleep, but I know I had this kind of arrhythmia I didn't know before. So it's going to be really amazing to get that data. We are trying to get that data, and it's going to be an amazing next step for us. Hopefully, we'll be able to get that data. Thank you.
All right, last. Okay. All right, let's thank our speakers one last time.